just dawned on me, though, that I know a couple of you at least are going on the trip with Dr. Olson. Yes. That's on the 14th. Is that right?
Is that the slew?
Oh, yeah, the slew one, yeah. That's on the 14th, yes? Okay. Advising day is on the 12th, which means that we wouldn't have class an entire week. So we may need to do something at some point to try to make up for at least some class time in there, just to make sure that we all are on track to get some things done. We'll see. We'll talk about it a little bit more as it gets a little bit closer. We got a month until that happens. So just I just thought of that this morning. We're going to have that entire week off. And by this morning, I mean, it just dawned on me like 3 seconds ago that it was going to be the entire week of lab off. Because they've moved it. It seems like they've moved advising back a week. Because usually it's on election day.
Yeah. Because we were very confused when we saw that.
Yeah. So, in any event, we'll figure it out. But it just dawned on me that, we'll have some missed class days. So, anyway. What questions do you have? Any questions at all? Ready to talk some more about ideals? Ideally not, right? All right. What's that? All right. So where we're going to head with the ideals today is we're going to create a new ring using the big ring and the ideal of it. We refer to that as a quotient ring. To get to that point, let's talk a little bit more about. Oh, somebody's coming in. There goes one. That's okay. To get to that point, we'll talk about the structure of ideals in the integers, and then connect that back to rings that we already know. It's a lot of noise. Connect that back to rings that we already know, and then we'll abstract that idea. So that's where we're headed. So in any event, hopefully it'll make sense as we go along. All right. So to do this, to start this out, let's let I be an ideal of the integers. And what we claim is that I is a principal ideal. What do we mean by principal ideal again? We talked about this last time. Oh, I'm going to shift the door because otherwise I'm going to be distracted. What do we mean by principal ideal again?
Very in charge of its students.
Sure, it's in charge of its students, or and it has a really good moral compass. It's principal. Principal, but okay.
Is it something in the ring multiplied by something else in the ring?
Okay, so the idea behind a principal ideal is that it's generated by a single element, right? So remember that when we have a principal ideal generated by an element, this is the set of all multiples of that element. Have to be a little bit careful. When I write it this way, I really mean that I'm doing this in a commutative ring with identity. We had a little bit of a discussion, right? If it's not commutative, then I have to do all multiplications on the left, plus all possible multiplications on the right, plus all integral multiples of the element, meaning add it to itself that many times, right? But if we have a commutative ring with identity, this works for the definition. And since we're talking about ideals in the integers, I certainly, bless you, certainly talking about ideals in a commutative ring with identity. All right. So first, let's eliminate one case pretty easily. why is the 0 ideal a principal ideal? What generates the 0 ideal? 0. Yeah, 0 does, right? 0 times anything is 0. So first, if I is the 0 ideal, or just the ideal containing 0, then I is certainly the principal ideal generated by 0. Right? The reason that works is because anything times 0 is 0, right? Like I mentioned last time, that's pretty universal in any math class that you'll come up with. 0 times anything is 0 is pretty universal, right? When we're actually talking about doing multiplication in a ring sense, 0 times anything is 0. Now, it might be the case that you have other weird types of multiplication, but that weird type of multiplication does not generally come up with 0. I use generally because I don't know of all possible cases, but I've never seen a case where 0 times something was not 0. And when we mean 0 to mean what we always mean 0 to mean. All right. So now let's suppose that I is not simply the 0 ideal. My first claim here, and I'm going to write this as a question. Why does I contain positive integers? Not all of them. I'm just saying, why does it have some positive integers? Why do I know no matter, as long as it's not the 0 ideal, then why do I know I definitely contains at least one positive integer in it? So I'm just saying there's something in there besides 0, right? Ideals have to be non-empty. So I'm saying it has more than just 0 in it. Remember, 0 has to be in any ideal, right? If it definitely has something else besides 0 in it, why am I guaranteed there has to be something positive? Well, if an element is not 0, it's either positive or negative, right? So what if I start with it? What if I start with a negative? Well, if I have a positive element in there, then I'm done, right? So what if I start with a negative element? How can I guarantee there will be a positive element also in there? So let's think back just to what it needs to be an ideal. What are the two big things that you need for ideal?
That all elements can be multiplied. Like that you could take an element outside of the ideal and multiply it with an element in the ideal and it's still be in the ideal.
Exactly right. So it's closed under subtraction and it absorbs multiplication, right? So it's a subring with a better, like you said, it's a subring with even better property with multiplication. And as long as you start with something in the ideal, any multiplication with that element, whether it's in the ideal or not, is back in the ideal again. It's like a sponge, right? It absorbs multiplication. So thinking along those lines, if I start with a negative element in I, how could I guarantee there will also be a positive element in I? What do you need to do? We can multiply by itself, then it has to be back in there again. I can also multiply by -1, right? I can multiply by anything, correct? So if x not equal to 0 is an element of I, then either x is positive or -1 times x is positive. In either case, I must contain a positive number. Because again, I absorbs multiplication. So you really just it's a shorthand way to say it absorbs multiplication from or by any ring element. Absorbs multiplication just means that start with something in I can multiply it by anything, and it's back in I again. Like I said, it's like a sponge. There was, or I'm sure it still is, but there was a person who used to write a math cartoon that was called The Brown Sharpie, and talk about the ideal sponge in one of the cartoons. All right, so we okay with the fact that I has to have some positive numbers in it if it's not the zero ideal? Okay, why am I making such a big deal about that? Well, I'm trying to generate I by some integer. So I have to figure out what that integer is that creates it. Okay. Well, way back when, or perhaps, I don't know where you are in discrete right now, perhaps recently, or you will, there's a property of sets of positive, subsets of the positive integers called the well-ordering principle. Remember what the well-ordering principle is?
We talked about at the beginning of this class.
We did talk about it at the beginning of this class.
Isn't it when it like goes up in order
Oh,
of like smallest to biggest?
Okay, so the smallest part is the important part. So every subset of the positive integers,
there exists at least.
there exists a least element, right? There is something in that is the smallest. All right, so let's let S be the set of all x in I such that x is greater than 0. This is a subset, certainly. It's a non-empty subset of the integers. The well-ordering principle tells us there exists, what letter do you want to call it?
D.
D? Such that D is the least element of S. Okay, so again, just to go through why we needed all these parts. Okay. Part of this is I want to focus on why we had the proof technique that we're doing. All right, so first I eliminated the case where we had the 0 ideal. Because if I want to use the well-ordering principle, I have to talk about a non-empty subset of positive integers. This is what the well-ordering principle says, right? 0 is not positive, so I needed to throw that case out first. Second, I needed to argue that we really always had positive numbers in my ideal because I need a non-empty subset of the positive integers, okay, to be able to use the well-ordering principle. So that's why I did those two cases, right? First, I eliminated the case where we had just the 0 ideal. And then second, I needed to make sure that if I have a general ideal in Z that's not the 0 ideal, it definitely has positive numbers in it. Okay, that's why we talked about both of those things. Now we're going to pick out this least element that we have. And our claim is that this element will generate all of I. The least positive number that is in I generates I, is what we're claiming. Okay. Well, how are we going to show that? Well, remember, to show two sets are equal to each other, we need to show that one's a subset of the other and vice versa. That's our general proof technique, right? All right, so always dangerous to use that adverb. Clearly, the ideal generated by D is contained in the ideal I. Why is that true? Since it's clear, we should be able to say, hey, why is that true? Remember again, what's the definition of the ideal generated by D? The principal ideal generated by D, what's that definition again? All multiples of D. What set in particular does D live in? Is in S, and S is a subset of I, right? So D definitely lives in I, and what do we just say that is one of the two defining characteristics of being an ideal? It absorbs multiplication. So if D is the set of all multiples of D, and D is in I, then all multiples of D are in I. So certainly we have that subset relationship. That's why it's clear, right? So that usually in math, when people something says it's clear, it better be a really, really short proof to prove it, or it's not very clear. So usually people don't mean that it's clear and obvious. Really, it means it's clear because it's easy to write down quickly. Easy always means quickly written down, not necessarily that it's actually easy. Okay? So the reason why this is clear is this is a set of all multiples of D. D lives in I, which absorbs all multiples of all elements. The end. That's why this is contained in here. All right, we need to go the other way. To go in the other way, to show something, one set's a subset of the other, we start with an element in that set and show that it has to be in the other one, right? So now let's I'll call it Y be in I. All right, now we've obscured everything that's going on by a lot of words and a lot of symbols. Let's go back to where we started. I want to show that I have an ideal of integers. And I want to show that that ideal is the set of multiples of some integer, right? So if I go back over here and I start with my I, an element in I want to show that it's a multiple of D. So what do you think we want to do with Y and D? I want to show that Y is a multiple of D, or think about it the other way, I want to show that D does what to Y? Divides, right? So I probably want to try to use the division algorithm and see what happens. Okay, I want to divide Y by D and see what we get. Okay, so by the division algorithm, what does the division algorithm tell us again? Well, think back to grade school. When you divide one number by another, what two things do you typically get? A quotient and remainder, right? That's exactly what the division algorithm tells us, right? There is a quotient, there is a remainder. Both of those things have to be unique, right? There's one quotient and one remainder, as long as your remainder satisfies what quality? There is a condition that the remainder has to satisfy. And what is it? It has to be less than the number you're dividing by, and it also has to be greater than or equal to. Greater than or equal to, not quite 1. It's a little bit less than that. 0, yeah. Right? Okay. So by the division algorithm, there exist unique integers Q and R. Remember again, if we use the there exists symbol and then put an exclamation point behind it, it means there exist unique integers Q and R exist. And then I have integers Q and R there such that Y is equal to, or it is DQ plus R, with R being greater than 0 and less than D, not N. Dividing by D. You just told me a minute ago that we want to show that D divides Y. So what do we want R to be? 0, right? So here's how we're going to do that. What do we know for certain? We don't know that R is 0 yet, but from the division algorithm, we know for certain that R is what? We don't know that it equals 0 yet, but we know for certain that it is. It's at least 0 and it's definitely less than D, right? How did we select D? Yeah, it's the smallest thing that's in S, right? Or I'm sorry, it's the least element of S, which means it's also the least positive element in I, but it's definitely the smallest thing in S, right? Okay. So what would have to happen if this were positive? Well, let's see if we can get this thing to be an S, right? How can I rearrange this equation to have R equal to something? What do I need to do? Just subtract. Good. So subtract. Let's see what we have. Where does Y live? In I. Where does D live? And I. Q times D then lives in I. Something in I minus something in I lives in I. Yeah, good. So this is in I, right? Y is an I, D is an I. So DQ is an I, Y minus DQ is an I, because we have ideal. Okay? All right. If R is greater than 0, then where does R live? I have an element of I that's greater than 0. Where else does it live? In S. Then R is in S, and R is less than D. Can that happen? No, because what's true about D? Or what's true about D? It's the least positive element of S, but I just found a positive element of S that's less. That's a contradiction, right? All right, so if R is not greater than 0, then R actually has to be equal to 0. If R is equal to 0, then Y is a multiple of D, or D divides Y. So that is actually in our ideal generated by D, the principal ideal generated by D. Thus, I is equal to D. So what this tells us, and there's a whole reason why I'm going through all of this. Well, there's actually a couple of reasons why I'm going through this, but there's a bigger reason why I'm leading into abstracting this. But this tells us that absolutely every single ideal in the integers is generated by a single element. So there's a special name for this type of ring. So the integers is an integral domain, the set of integers is an integral domain. Since it's a principal, since every ideal is principal, we refer to this as the ring Z is called a principal ideal domain, or a PID for short. There are other examples of principal ideal domains. We won't see too many of them, but there are other examples of them. Principal ideal domains turn out to be pretty nice. For example, anytime you have a ring that's a principal ideal domain, it's also what's referred to as a unique factorization domain, which means that everything factors exactly one way up to reordering. And units are never included in factorizations. That's why we always talk about prime numbers being positive. Because you can also have negative primes, but you just take off the negative and then it corresponds to the positive thing. Okay. We don't worry about units in factorization, but principal ideal domains are always unique factorization domains. So that's a nice structure thing from a factorization standpoint. And you're used to doing factoring, right? You did factoring in grade school with numbers, you do factoring in algebra class with polynomials, and that factorization is a huge topic all the time, because what are you trying to do? Take a complicated problem and break it down into simpler pieces. So factorization stuff pops up all over the place. So that's why it's a whole field of study. All right. So in any event, that's what we have. All right. Why do I care? Holy cow. I just went through a long-winded thing to go through all of this. Why do we care? Okay. So we've already talked about generating Z mod M idea or Z mod N ideas, right? Integers modulo a number. So we want to get to that point of trying to see how we can create those rings in a different way and then abstract this whole idea of ideal. So we've talked about congruence modulo a number, right? Right. So in particular, if we write this as a division statement, if we want to say A is congruent to B mod N, as a division statement, what does that say? Yeah, n divides A minus B, right? And if n divides A minus B, that means that n times something is A minus B, right? That's what the divide statement means, right? I should say for some integer y. But now, if we say this in the language of ideals, we now have a multiple of n. So I can say that A minus B is in the ideal generated by n. Because the ideal generated by n is the set of all multiples. So if A minus B is a multiple of n, then that difference must be in the ideal. So all we've done all of this to start with, right? This is all new, this is all old stuff that we've already talked about. This is the only new step, or we're just using the language of ideals to say the exact same thing. But this statement here is the one that we're going to abstract to an arbitrary ideal, not just principal ideals in the integers. Okay? So let's let R be a ring, any ring, and let I be an ideal of R. Then for elements A, B, and R, we say A is congruent to B modulo I if and only if A minus B is in the ideal. We write the exact same notation we do for congruent mod N. We'll write mod I that way. The book puts parentheses around it. I don't really care about the parentheses around it. You can put parentheses around it. It's the same notation. Put parentheses around the mod I or not, doesn't matter. Okay. So it's the exact same notation. So this abstraction really does come from the structure of the integers. We've already talked about congruence modulo a number, but we can think of that now as being the difference of the two elements being in an ideal, so we're just abstracting it to any ideal. Now, if it's going to be an honest goodness abstraction here, then it better satisfy the same things as being an equivalence relation or a congruence relation, either or. So it should be reflexive, symmetric, transitive. Okay? All right, so let's show that this congruence, oops, I'll give you the number that's in the book here too. It's theorem 6.4. I'll just write it this way. Congruence modulo an ideal is an equivalence relation. All right, so let's go through the three pieces that we have to prove to show something is an equivalence relation. We now have to do reflexive, symmetric, transitive. How do we show, what do we need to show something is reflexive? Yeah, it's congruent. Any element of the ring is congruent to itself, right? So let's let, I'll call it A, B, and R. Congruence modulo an ideal says that when you subtract the two elements, I'm back in the ideal again. So if I want to show that A is congruent to itself, I need to subtract A from A. What do we get when we subtract A and A? 0. And where does 0 live? Well, it lives in R, but even better, it has to live in I, right? It has to live in any ideal, right? 0 always has to be in your ideal, no matter what ideal you're talking about. Which is, and this is exactly the definition of being congruent modulo the ideal. So A is congruent to A mod I. What do we start with to show that a relation is symmetric?
A equals.
No, you can
Go for it.
A is congruent to B and B is congruent to A.
Yeah, so if A is congruent to B, then B is congruent to A. That's what we need to show, right? So now let's suppose if we let A, B, and R with A congruent to B mod I, right? We need to show that B is congruent to A. So let's just go through the definitions. A is congruent to B mod I by definition means what? Good. What do we want to show as an I? B minus A. So how can I get to that? Yeah, multiply by -1, right? It has to be closed under multiplication. Also has to be closed under inverses, right? That's another way to think about it. So if I do the inverse of A minus B is an I, or B minus A is an I. Hence, we have flipped it around. What do we start with for transitive?
If A is congruent to B and B is congruent to C, A is congruent to C.
Good. Yep. So let's start with A, B, and C in R. with A congruent to B mod I and B congruent to C mod I. By definition, what do we have now? Good. What do we want to end up with? So what should we do? Yeah, add them, exactly. We want to end up with A minus C being an I. I've got a minus B in the first element and a plus B in the second element. So add them together, they're going to cancel. All right. So A minus B plus B minus C is an I, or A minus C is an I. Hence, A is congruent to C mod I. Okay. So far, so good. All right. Notice that these are, I mean, this is almost the exact same proof we did for congruence modulo n. We've just changed it to the language of ideals, right? So we've abstracted it from being a very specific property in the integers to being a property that any ideal has that we can do this. Okay. All right, any questions so far? You know, things got abstract kind of a hurry in this particular chapter. All right. So the proofs are going to follow the same types of proofs that you do for congruence mod n, so I'm not going to belabor them here. But if I is an ideal of R, and we have A congruent to B, I guess I probably need a comma here. A congruent to B mod I and C is congruent to D mod I, then A plus C is congruent to B plus D mod I, and A times C is congruent to B times D mod I. Like I said, the proofs are very similar to what we did before. With the integers, with mod n. So, rewriting them as subtraction statements again. For the first one, I was going to talk through, I'm not going to write it down, because like I said, it's very similar. You would write this as A minus B as an I. This one you'd write as C minus D as an I, and then add the two together, it's still an I, and just rearrange your sum. Right? The multiplication's a little bit trickier, if you will, because I would need to multiply the first equation by C, and the first A minus B by a C, and the second one by a B, and then add to the terms in the middle cancel. We did that before too, just have to do an extra step, but it's the same proof. So if you go back to your notes of doing congruence modulo n with those two pieces, you should be able to see how to extend that to proof mod I. It's the same kind of thing. All right. The reason why we want to show these congruences is because notice that we're talking about defining an addition and defining a multiplication essentially here. And want to make sure things are well defined. Okay. What we're going to do with these particular properties is we're going to create a new ring from an old one. Okay. That's the idea here. Right. All right. How are we going to create this new ring? Well, we're going to create this new ring by using something that's referred to as cosets, We're going to do this now, and we're going to do this when we talk about groups later on. So, as a definition here, if I is an ideal of R and A is an element of R, then the coset of A with respect to I, I'll call it that way, is defined this way. We write it as A plus I, and we just create all the sums that we can. Fixed A, add it to everything in I. That's what we mean by a coset with respect, the coset of an element with respect to I. We've done this already, we just haven't called it this before. Okay, let's talk about why we've done this already. I'm going to write it differently, but you've already done this. This is not new. This is just new notation. Okay? We talk about generating all the cosets. This says add 0 to everything, right? That's what this says. Right? Okay? So when we add 0 to everything, I just get all the multiples of 5, right? We agree? The ideal generated by 5 is a set of multiples of 5, right? What do you get when I do 1 plus I? What do we get when we add 1 to everything? Well, I certainly get a 6 here. This one becomes, because I'm going to add 1 to it, right? So it'll be 1, 6, 11, 16, negative 4, negative 9, negative 14, right? Because we're just adding 1. And we get the same thing if we do 2 plus, similar things if we do 2 plus I, 3 plus I, 4 plus I. These should look familiar, right? What did we call these before? Back when we did congruence modulo a number, what did we call these before? We didn't call them cosets. What did we call them? Okay, let me ask a different question. Let's look at these pieces individually. And in particular, look at these numbers right here. The ones that I just put a little circle around. What are those relative to 5? What are those? The remainders, right? The possible remainders, correct? So what we have in each of those sets are the things that have 0 remainder when you divide by 5, 1 remainder when you divide by 5, and so on. What did we call those before? Equivalence classes, right? This is your equivalence class of 0, of 1, of 2, of 3, of 4, right? Like I said, we've done this before for congruence mod n. We're just giving it a different name, right? So these are equivalence classes, right? In this very, very specific case. notice that if I notice that they really are equivalence classes, right? They have no overlap, they're unions, everything. Here's something else to notice. If I take, let's do 1 and 3, for example. If I take anything in 1 plus I, or this class, and add it to anything in this equivalence class here, where do I end up? If I take anything in this equivalence class plus anything in this equivalence class, what do we end up? In the fourth one down here, right? Doesn't matter what we use, right? I can take 16 and add it to negative 12, I get 4. I can take negative 9 and add it to negative 7 and get negative 16, which would be the one that's not, the next one that's not listed here, right? So if I take anything in here and anything in here, I get anything in here, which makes the addition well-defined in Z mod 5, right? Because what do we say? 1 plus 3 is 4, right? Or 3 plus 4 is 2, right? 7 divided by 5. But notice again, it doesn't matter which representative we use. So if I want to do the 3 plus 4 is the 2, for example, 8 minus 6 gives me the 2, but 13 plus 14 is 27. 27 would be in this equivalence class up here, right? It doesn't matter what element you use to represent the equivalence class, the addition is still well defined. That's where we're going to go with these cosets for any ideal. So to get to that point, pardon me, actually we already got to that point. This is what makes that addition well defined. And then the same thing with the multiplication, right? A represents the same thing as B, and C represents the same thing as D. Well, if I add A and C together and add B and D together, add A and C and B and D, I get the same thing because I started with the same things. I better end with the same things. In any event, what we're doing here is these cosets actually are equivalence classes. So this is theorem 6.6. We say that A is congruent to B mod I if and only if A plus I and B plus I are the same cosets. So cosets end up being equivalence classes modulo an ideal. Okay. And the idea behind this is the same kind of proof anyway. They even mention this if you go through the proof of theorem 2.3 and just change all your equivalence class notations to coset notations, you get the exact same proof. So the book even says, and I'm going to write the same thing, is compare this of theorem 2.3 to this one. I mean, we didn't write down the proof, so I guess saying compare is the wrong word, but go look at theorem 2.3 and see if you can change the proof to get the proof of this one, is what I mean. Compare is probably the wrong word, but I'm going to use it anyway since I wrote it down. Couldn't possibly erase it. All right. In any event, what we really have are equivalence classes. If we have equivalence classes, we know from equivalence relation things that equivalence classes are either disjoint or identical, right? There's not non-trivial overlap between equivalence classes, right? That's one of the properties of being an equivalence class is that it partitions up your set, right? The union is everything, and the intersection of any two is empty, right? So that's just being an equivalence class in and of itself. All right. So where does this go? Well, this takes us to the idea of 6.2, which talks about quotient rings, and then brings back homomorphisms. Yes, I know. All right. All right, so let's go back to, go back to what we did with easier times, even though I'm writing it in a new notation. Okay. All right, so I've got my R and my ideal being generated by 3 on the left. On the right, I've got Z3. We've already talked about Z3, right? Okay. So over here in Z3, we had an addition, and a multiplication. If I can write my multiplication down correctly. And that was what we got, right? Look familiar? I hope. Okay. All right. Let's go back over to the new thing. First, let me ask you, what are the cosets of all the cosets of I? First off, we always know that one of the cosets of I is going to be I itself. What do I do to generate that coset? What would I add to I to generate just I back again? What element of R would I add to the ideal I to get the ideal I back again? 0, right? So one of your cosets is this one. Right. That's one coset, right? What's another coset? What could I add to I and generate another coset? 1? Cool. What's another element I could add to I and generate even a different coset? 2. Again. Now, once I've done that, is there anything else that we could possibly add and generate something different? No, we've taken up everything, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We've taken everything up in the positive and the negative direction, right? So there aren't any more distinct cosets. I can generate more cosets, but it's going to be one of those 3. There's only 3 distinct possibilities, right? Okay. So here's how we're going to create what I'm going to call a new ring. But the whole idea of this is it should look like the old ring, okay, that we already know how to talk about. So here's how we're going to create the new ring. I'm going to use these 3 elements as the elements of my new ring. And I'm going to talk about how we add them. And how we multiply them. Now you might, hopefully you've kind of got the idea of what I'm gunning for here. But let's think about, generally speaking, how we might want to add these things together. And I said this a little bit ago. When we were back up in that original thing where I started writing out cosets, I said that if you add anything in, say, 1 plus I to get, or I'm sorry, try that again. add anything in 1 plus I to anything in 3 plus I, we got something in 4 plus I, right? We agree? So thinking back to that example, what do you think we would define 1 plus I and 3 plus I to be? So if I take anything in 1 plus I and anything in 3 plus I get something in 4 plus I. What do you think we would define 1 plus I and 3 plus I to be? 4 plus I, yeah. How do we get from 1 plus I to 3 plus I? Well, 1 plus 3 gives you 4, right? So that's exactly what we want to do over here is just define adding cosets is by adding cosets to be adding coset representatives. Okay? So here I would have 0 plus I, 1 plus I, 2 plus I. Here we would have 1 plus I, 2 plus I. Okay, well, I said just a second ago, we probably want to add cosets, the definition being as adding coset representatives, right? Well, if I do 1 plus I and 2 plus I get 3 plus I if I just add the coset representatives, correct? 3 plus I isn't in my list. But if I think about generating a coset using an element, the coset generated by 3 is the same thing as the coset generated by what? 0, because they're in the same coset, right? So this one, I would get 0 plus I. So what do you think the next row would be? 2 plus I, 0 plus I, and 1 plus I. And notice, to get the 1 plus I, when you do 2 plus 2, you get 4, but 4 generates the same coset as 1 does. So 1 plus I and 4 plus I would be the same thing, because they're in the same coset. Over here, you can probably guess how we're going to fill out our multiplication table. If I said, when you add cosets, you add coset representatives, what do you think you're going to do when you multiply? Just multiply the representatives, right? So we should get 0 plus I, 0 plus I, 0 plus I, 0 plus I, 1 plus I, 2 plus I, 0 plus I, 2 plus I. The last one again, though, when you take 2 times 2, you get 4. But 4 plus I is the same coset as 1 plus I. And do you see any relationship between the addition and multiplication tables that we just formed and the addition and multiplication tables for Z3? Yeah, they're literally the same. When you see the same addition and multiplication tables, we say that the rings are isomorphic to each other, right? So what we created over here on the right, the left thing is we created the quotient ring. We write it as R mod I. That's what we mean by quotient ring. This is the set of all distinct cosets where we've defined addition as add coset representatives, and we defined multiplication as multiply coset representatives. That's what we just created, was called the quotient ring. So your elements in the quotient ring are cosets. We're adding cosets and multiplying cosets. The way we do that is create the the sum of cosets is the coset of the sum of the representatives, and likewise for the product. Now, the issue is that we need to make sure things are well defined, right? Because this is dependent on what representative we picked, right? So a second ago, we said when we did two, the way this definition would work in the one we just did a second ago, the definition says this should be 4 plus I, right? But we wrote down that it was the same thing as 1 plus I. Yeah. The reason why we can do something like this is because we have that equivalence notation idea, or the equivalence relation idea, that the equivalence class of 4 is the same as the equivalence class of 1. So I can just choose a different coset representative. The idea, though, is that for any of these things, it should be independent of representative that you pick. Now, I know this sounds weird, but you've done it since grade school. What I mean by that is, these are equivalence class representatives. These are actually equivalence class representatives. You never called them that in grade school, right? But they are, correct? What did you do in grade school when you wanted to add these things? Get the same denominator. You use a different equivalence class representative, right? Yeah? Yeah, that's what we did, right? But you should have got the same answer if you used a different equivalence class representative, right? Like, is 6 the only denominator you could use? No, as long as they're the same, you could always combine them, right? So you could have used 6 twelfths and 4 twelfths, and then make sure that you really do have the same answer because they generate the same equivalence class. The things that are equivalent to 10 twelfths are the same things that are equivalent to 5 sixths, right? So this is just an extension of things that you've done since grade school. I know it sounds weird, but you've done this in grade school, just you never wrote it like this, right? You could convert it this way if you really wanted it to. I'm not suggesting that you do, okay? But just to write this down, I can do ordered pairs where I don't let my second element be 0, right? I'm going to let, how do I do this? Make sure I don't do this wrong. Oh, I can do it with a relation. I'm going to have a harder time with my ideal. But your relation I can define a relation on that. What did I do? What is, thinking of fractions, what is this? If I think of this as a fraction, I cross multiplied, right? This is how you define your rationals. Okay. You can do the same kind of thing. I can create an ideal where I can get this equivalence relation and then do these as basically cosets in this case. In any event, that's not what we're going to do here. But you've done this, like I said, you've done this since grade school. You just never called it this, right? All right. In any event, this is how you create a quotient ring. All right. So we also said, notice that this was isomorphic to Z3. So what we notice here is that write it this way. Z mod out by the ideal generated by 3 is the same thing as the Z3. By the way, we generally call this modding out by an ideal as opposed to modding out by a number. Let's do another example that's maybe slightly more difficult, but maybe it'll illustrate what's going on a little bit better. So let's let R be this ring. What's this ring going to be? We have the brackets X. We're talking about what type of objects? polynomials, and all the coefficients are coming from where? Z mod 2, right? So the only coefficients that you're going to see are what? 0 and 1, right? Okay. So we're going to let R be that set of polynomials, and let's let I be the ideal generated by x squared plus 1. Not x squared plus 1. Sorry, I lied. X squared plus x plus 1. I want to illustrate a different property here. All right, so now let's think about what are the distinct cosets of I. All right. Well, certainly one of the cosets of I is always going to be the coset that's generated by 0, right? I is always one of the cosets, right? So one of them is 0 plus I. And I'm not going to try to write out all these polynomials, by the way, because there'd be a lot, correct? Okay. But the idea here is to try to come up with different ones, okay? I want to see how many different ones I can come up with. Because I want to create this quotient ring, all right? I want to try to create this R mod the ideal. Let's go back up to this example here. We're taking Z and modding out by the ideal generated by 3, which basically says that every multiple of 3 is equal to 0, just like it is in Z mod 3, right? So what we're doing when we mod out by an ideal is essentially saying that's everything that's equivalent to 0, right? That makes sense? That's everything that's equivalent to 0. So over here, I already erased it. Up there, for example, if I wanted the ideal for everything to be equivalent to 0, I would use the ideal that was 0, comma, anything in Z star, anything that is non-zero. And that would be all the things that are equivalent to 0. Mod out by that thing, and you can generate all the rationals. Okay. All right, so anyway, think of anything in the ideal as being equal to 0. Think of it as equal. Literally, this is kind of the right way to think about it as you're starting. So if I treat 3 as 0, then the only number possibilities I get are 0, 1, and 2, right? So let's go over here. Anytime I see x squared plus x plus 1, I'm going to think of that as 0. Okay. Well, let's maneuver some things around. Subtract your x plus 1 to the other side. I get x squared equals negative x minus 1. But where do we say all our coefficients are coming from? Mod 2. So negative 1 is the same thing as 1, right? So really I can write this as x squared equals x plus 1. Now, technically, this is not what we have, okay? But this is the right way to think about it. And what I mean by that is mod this ideal, x squared is the same thing as x plus 1. So anytime I take out, if I have an x squared, I can immediately knock it out with an x plus 1, right? So if you had something like x times x, let's start with x cubed. Well, that's x times x squared. What did I just say I could knock x squared out with? X plus 1. Distribute. But again, what did we say we could knock out the x squared with? X plus 1. And now x plus x is 0. And 2x with 2x is 0. We end up with 1. Nothing special about x cubed. I can do the same thing with x to the 4th, x to the 5th. I can always knock it down to a constant plus an x. Constant is 0 or 1, x is 0 or, well, the x coefficient has to be an x, right? I can't get I don't have any other higher powers, because this relationship lets me knock them down. They're not equal. What I'm equating are the things that generate the same cosets. Okay? And in particular, I'm thinking of this generating the same coset as 0, so x squared and x plus 1 would generate the same coset. So back to where I was to figure out my other cosets. I don't need to use x squared or higher, right? Don't need to use x squared or higher. So what are my other possibilities for cosets? What are the only other possibilities for polynomials if I throw out x squared and higher?
Just x plus 1 or 1.
Or
X.
x, right? Those are the other possibilities, right? So my other, these are the only possibilities for possible cosets, right? This is it. Now, I should make sure that they really are distinct from each other, right? Agreed? And we need to make sure they're distinct cosets. But if they were the same coset, if 1 plus I and x plus I is the same coset, I'll write this off to the side here. 1 plus I equals x plus I. That tells us that 1 minus x is in I. Right? We agree with that? But 1 minus x is the same thing as 1 plus x is in I. Agreed? Okay. So, is that true? Well, our ideal is that, right? We agree? Okay. Ideals are closed under subtraction, right? Or they also absorb multiplication. Well, can I multiply? So my coefficients are coming from Z2, which is a field, which in particular is an integral domain. Can I multiply this by a polynomial where the elements are coming from a domain for the coefficients and knock down the degree? So what I'm saying is that if I had like an a x to the m and a b x to the n, is there any way to get 0 out of that if these are coming from an integral domain? No. Okay. If this is a non-zero element and that's a non-zero element, I can't knock down the degree, right? The degree can't go down. It can only go up, right? So I can't get 1 plus x by doing multiplication, right? And that's exactly how we generate this, isn't it? I multiply this by elements from R. I can't knock down the degree, so can this be in here? This can't be a multiple of that. It's too small, right? So this can't happen. And then likewise, if if I add these two things together, well, 2x ends up being 0, I end up with 1. If I subtract these two things, I would get, is this the same thing as that? Well, no, I wouldn't be able to have that because I would have 1 as in my ideal, which is bad, right? Try that again. If x plus 1 plus I is x plus I, this would imply that the difference is back in I. It says the identity is in I. What did we say? If the identity gets an I, then what does your I happen to be? End up being? In particular, if a unit ever gets in your ideal, what does the ideal do? Second defining characteristic for being an ideal? Absorbs ring multiplication. So if the identity is in your ideal, what happens? The ideal is the whole ring, right? It absorbs the whole ring. Is this the whole ring? Is this every single polynomial from Z2 of x? No. Okay. the whole goal of that was to say that these really were distinct cosets. Okay. So what I'd like you to look at for next time, I'm not going to give you new homework. These are the distinct cosets of I. There's 4 of them. Okay. I want you to create the addition table, create the multiplication table for next time. Just like what we did with the first example. I think addition will be fairly straightforward. I think multiplication will be a little bit trickier. Not bad, a little bit. You don't have to do that many multiplications, okay? But in your head for multiplication, keep this in mind. Every time you have an x squared, you can replace it with x plus 1. That'll help you fill out your multiplication table. Okay? So do that for next time. We'll talk more about this next time as well. I know, it kind of got hard, right? I know. This is why I said I tried this different book for this, and it just is not, it's not the order I would have gone in. This is harder than I would want at this point in the semester. So, we'll deal with it. Maybe it'll make the end of the semester easier.
Yeah.
Yeah, look on the bright side.
I thought we were pushing everything off to the
But that is true. We were pushing everything off to the side. But it'll be easier, but a lot?
Yeah.
Yeah. Okay.
Yeah.
Yeah. Okay. I'll see y'all later.